Good morning, champ. Today, we're taking another big step in understanding how change works. We've already mastered separable equations, the ones that let us split x's and y's cleanly. But not every real-world system behaves that neatly. Many problems in physics, finance, and engineering lead us to linear differential equations. They look simple, but they model a huge range of systems, from electric circuits to population flow. Let's see what makes them linear, how to solve them, and why the trick called the integrating factor is such a game changer. A first-order linear differential equation has the form y prime plus p of x times y equals q of x. Here's what each term means. Y prime is the derivative, how y changes. P of x multiplies y, showing how the rate depends linearly on the current value. Q of x is the forcing function, the external input or influence on the system. If q of x equals 0, we call the equation homogeneous. If q of x is not 0, it's non-homogeneous, meaning something external is driving the system. All right, champ. Here's the strategy. We can't separate variables directly, but we can multiply the whole equation by a special function that makes the left-hand side become a perfect derivative. That function is called the integrating factor, written mu of x. We choose mu so that mu times y prime plus mu times p of x times y equals the derivative of mu times y. That means mu prime equals p of x times mu. Integrating that gives mu of x equals e to the integral of p of x dx. Once we have mu, we multiply the entire equation by it. The left-hand side collapses into the derivative of mu times y, and we get the derivative of mu times y equals mu times q of x. Integrate both sides. Mu times y equals the integral of mu times q of x dx plus c. Finally, divide through by mu to isolate y. That's your general solution. Y equals 1 over mu times the integral of mu q dx plus c over mu. This formula works for every first-order linear ODE. It's your universal toolkit. Let's see it in action with a classic physical example. Newton's law of cooling. We'll solve y prime plus 2y equals 10 with y of 0 equals 0. Here p of x equals 2 and q of x equals 10. Compute the integrating factor. Mu equals e to the integral of 2 dx, which is e to the 2x. Multiply through by e to the 2x, e to the 2xy prime plus 2e to the 2xy equals 10e to the 2x. Now recognize the left-hand side. That's exactly the derivative of e to the 2x times y, because the derivative of e to the 2xy is e to the 2xy prime plus 2e to the 2xy. That's the key moment. The integrating factor makes the whole left-hand side a perfect derivative. So we rewrite the equation as the derivative of e to the 2xy equals 10e to the 2x. Integrate both sides. On the left, the derivative and the integral cancel, leaving e to the 2xy. On the right, the integral of 10e to the 2x is 5e to the 2x plus c. So e to the 2xy equals 5e to the 2x plus c. Divide through by e to the 2x to get y equals 5 plus c e to the negative 2x. Now apply the initial condition y of 0 equals 0. Plug in x equals 0, 0 equals 5 plus c, giving c equals negative 5. Final solution, y of x equals 5 times 1 minus e to the negative 2x. As x increases, the exponential term shrinks towards 0, and y approaches 5. That's the steady state temperature difference, the equilibrium. This is exactly how an object cools or warms toward its surroundings. Now let's solve another one, this time with variable coefficients. We'll solve y prime plus xy equals x. Here p of x equals x and q of x equals x. Compute the integrating factor. Mu equals e to the integral of x dx, which is e to the x squared over 2. Multiply through by mu, e to the x squared over 2y prime plus xe to the x squared over 2y equals xe to the x squared over 2. The left-hand side is again the derivative of e to the x squared over 2 times y. So we write the derivative of e to the x squared over 2y equals xe to the x squared over 2. Now we integrate both sides. The derivative of x squared over 2 is x, so the integral of xe to the x squared over 2 dx is just e to the x squared over 2. That's the reverse of the chain rule in action. When the derivative of the exponent shows up in front, the integral collapses neatly. So we get e to the x squared over 2y equals e to the x squared over 2 plus c. Divide through by e to the x squared over 2. Y equals 1 plus ce to the negative x squared over 2. The constant part, 1, is the particular solution caused by the forcing term q of x equals x. The exponential term ce to the negative x squared over 2 is the homogeneous solution. It fades out as x grows. So the complete solution is y of x equals 1 plus ce to the negative x squared over 2. Let's step back and see what's really happening. The integrating factor method is a clever way to reverse the product rule. By multiplying by mu, we combine y prime and p of xy into one derivative that we can integrate in one shot. Every solution to a linear first-order ODE has two parts: the homogeneous part, which fades out over time, and the particular part, which represents the steady-state response. Together, they describe how the system evolves from its starting point toward equilibrium. In our cooling example, the exponential part died out, leaving the steady value of 5, perfect thermal balance. So, champ, the integrating factor method is your Swiss Army knife for first-order linear equations. It works every single time, even when you can't separate variables.